And thank you, first of all, to the CDT management group for inviting me. It's a pleasure to be here. I've been to Leeds many times, but this is the first time I actually came the day before, rather than treating it as a one-day trip. And so that's the topic of my talk. And it's really interesting that someone like me and who used to work with commercial code and in industry and then academic code. And it's about 2005. I started with the OpenFOAM. I'm showing these funny images because that's how my journey with the OpenFOAM started. I took my postdoctor and to a terraced Victoria House in Reading and to visit the OpenCFD company. And that's the company just started, still in Harry Willis' house. It's amazing how much such a small company developed over the years. It's now international and it's bought by different companies and it's big organizations. So for myself, and certainly, and since 2005, and I had a lot of fun and with OpenFOAM and together with my researchers, and which came with that is also publications and grants, and I'm really pleased I've made the choice. But in the beginning, I was unsure. I had many questions, and especially whether the code would disappear or become a fully commercial code after a few years and no longer open source. But I was assured that there wouldn't be such a problem. So this is a photo shot of my group webpage, and it shows you the application area and we have been involved with. And I specialize in application of CFD to safety-related problems, especially those problems in industry. And with regard to the move towards net zero, a particular interest we have been developing since 2005 is hydrogen, and started with the gaseous hydrogen. And from 2006, I had a major European grant. And more recently, we are now working on liquid hydrogen safety. So I'm actually launching a joint industry project on liquid hydrogen safety, which will start next year. I cannot talk too much about it. And also I work with industry and the European partners on safety of lithium-ion batteries. And these are the batteries which are in our mobile phones and electric cars, and used for grid storage of energy, especially storage of energy and from excess wind power in low peak time, low times. And I'm still showing a fire picture here, fire in the built and the natural environment. I also have a few slides stuck in the end to quickly go through our work. That was my bread and butter in the beginning of my academic career. I was working from 1995 to 1990 to about year 2005, primarily on fire research. It was about 2005, I started entering hydrogen and then explosions and then safety and then carbon dioxide here. And what's shown here, pipeline is work and Mac favored here. And we were together in the Cooltran project funded by National Grid, where we looked at the decompression of pipelines and carrying the carbon dioxide captured from CCS projects. And so we had a lot of fun with that. We analyzed the decompression and we also analyzed the atmospheric dispersion of the released carbon dioxide. Another aspect of the work which we have done is I had a monocyte and Marie Curie PhD, which gave me 6 PhD students. And from 2014 to 2018, working on the safety of liquefied natural gas. I know I'm showing all these things, it's like the big pictures and what we do, but underneath each of these subject areas, and I have a key interest on developing physics-based submodels So no matter what projects I get, whether it's funded by industry, EPSRC or European Commission, I always take care that we put in some development and we enhance the code. Otherwise, why should they fund us rather than just giving people download the OpenFOAM and use it? We don't. We do download the OpenFOAM, but we have our own versions where we put our submodels in, and either it's for the physics, for the chemistry, for the transition, evaporation. So we do all those sort of things. And partly because of my interest, partly also to ensure that our publications from the group and for the benefit of the researchers, they do get into the top academic journals rather than industrial applications. So the majority of my talk will be based on hydrogen. I will talk about work in the gas hydrogen safety area as well as the safety of liquid hydrogen. And in the end, I hope to save some time to talk about the firewheels, which is my hobby, new hobby. And I don't need this animation. What I'm trying to say is in a potential accident scenarios, and we are moving now towards a hydrogen economy, and the hydrogen is going to be a major energy carrier. And in the transition to the later there, though, in that process, there's the production of hydrogen, and there's also the distribution and the transport, as well as the storage, and finally the utilization. Through that process, and the safety is paramount, because if there's accidental releases of hydrogen, whether it's gas or whether it's liquid, and there are various scenarios which can happen, as I illustrated here. And although hydrogen is really light, so it does have some benefit. So if it's dispersed quickly into the atmosphere, and that's good news. And whether it's liquid and evaporates quickly, and the liquid hydrogen, when it comes out, it evaporates. The volume expands by more than 800 times. So it's an enormous cloud. But if they can disappear more quickly into the atmosphere and without resulting ignition, then that's good. That's good news. But most of the times, because the wide flammability range and hydrogen requires very little energy to ignite, so you would end up with ignition. So you would either get jet fires or you get explosions, or with liquid hydrogen, you get a vapor cloud explosions. So all this can happen, and that is of concern, because for a hydrogen economy and safe transition to net zero, these safety issues, they need to be addressed. New installations need to be underpinned by safety cases, and that's approved by the regulatory bodies. And so I will start with spontaneous ignition, and it's less likely this will be in the UK, hydrogen-powered fuel cell cars, but we do have some demonstration example vehicles running around in the UK and more in the US. So typically in hydrogen fuel cell powered cars, and the hydrogen is stored in high pressure cylinders. And the Toyota Almera stores about 750 atmospheric pressure. So it's 75 megawatts. And also in the refuel stations, gaseous hydrogen under pressure, 100 bar, is still a currently commercial way of storing hydrogen, while liquid storage is another form. So under such high pressure, and the early work we did was found that if there's something released from a pressurized storage vessel, and those shock waves, and the shock waves, and the development of the shock wave, and in the front of that shock wave, and there's a hydrogen interaction with the air, there's a mixing, the molecular mixing at that level, it pushes the temperature up, and you can get spontaneous ignition, and all through a section of tubes, and in most applications, hydrogen doesn't come out suddenly from a crack. It's more likely it's the connecting pipes which are the weak points in the system. And if there's a rupture or something, hydrogen come out through a section of tube. So they are experimental as well as numerical simulations done by my group, and which does indicate that there's a great potential of spontaneous ignition in such situations. And so theoretically, it's possible, and experimentally, it's captured. And by experimentalists, and in the UK, HSE, and in Japan, in Russia, and in China. So there are various experiments. And but what's shown here is that if you look at the rupture time, and if it's 0, that's a sudden release. And if rupture time is 0.6 microsecond or 1.2 microsecond, that's we are trying to mimic the practical situations where you don't really have sudden release. It takes time for storage vessel to rupture. So what we found for direct release, in practice, it's unlikely to result in spontaneous ignition. The temperature at the front would go up, and but it quickly it went down. It's diluted by it's quenched and by the environmental flows around it, surrounding flows, and but in a situation which is more likely to be in practical situations and released through a section of tubes, and what we are finding that it's more likely because the shock reflection, and you see here the shock waves reflecting from the tube walls, and the heating of the front of a hydrogen air interface, and that's more likely to result in a spontaneous ignition, which can translate into a jet fire. So, which can translate into a jet fire, which is the next topic. But what I want to say is that behind all this and the animations you see here, we actually did a lot of development. And I should clarify, this part is not done with OpenFOAM. I forgot my title is OpenFOAM. I should clarify, this was done with the Kaiwa, the Kaiwa code, which was developed for internal combustion engine by Las Olmos Laboratory in the USA. The reason we did it with Kaiwa rather than OpenFOAM with that, it's to do with the key limitation of OpenFOAM. You cannot go in terms of numerical schemes, and it won't go anywhere above second order. Well, for this one, we need a high order numerical schemes. This is a Velo scheme, which we implemented into Kaiwa, and we tested the third order, fifth order, and the ninth order. And also, in order to capture these numerical simulations, we actually had to use very, very fine grids. So the grid resolution used in these simulations, they range from 5 microns to 10 microns, to 50 microns, to 20 microns. We tested a range of them, and against the classical scenarios where there are analytical results. So there's a lot behind these animations, and which I didn't talk about. And so what I have shown here, these are the advanced laser diagnostics, which researchers in Korea have done after our simulations. And we did those simulations about 2008, 2009, and so these were our simulations which we did in 2009, and afterwards, and researchers in Korea did experiments. So qualitatively, and we are capturing the phenomena which they saw, and the near wall ignition, and the shock focusing, and the transition from the spontaneous ignition to a jet flame. But we didn't make a quantitative comparison because the grant finished. The grant finished after they did the experiments. We moved to do other things for hydrogen. And one of the other things we did was jet fires. And can I ask the audience? You can cut short my question time if I ask the audience now. Looking at these two files, and which one do you think is a hydrogen fuel cell car? Which one is a gasoline? I'm not going to move my pointer. And if you think this one is gasoline, put your hands up. How many people think this car is gasoline? Nobody. That's really good. So I don't need to explain jet file, and I won't need to talk about this. What this is trying to show is how we treated the thermal radiation, and so I'm going to bypass these developments. And this is again a treatment of pseudo diameter treatment which we use. The reason we did that is we did a spontaneous ignition. I was talking about we were using 5 micron, 10 micron grids. When you go to a major file and the jet file, you can no longer do that. So we use a pseudo source and to bypass the shock region, and then we ignite the jet, which in practice quite often, most ignitions hydrogen, I think is still by sparks or even mechanical fixing, and rather than those diffusion-based spontaneous ignition. So, but the thing is, in most accidents, I was listening to some industry talks even last month, most of the accidents, it's not clear what caused the ignition, even to the operator. So it's a miracle there. So in jet file simulations, we don't do those shocks. We bypass them with simplifications. We start from a pseudo surface where the pressure has reduced to atmospheric pressure, so we can use larger grids. And we look at the flame length. We look at the radiation levels and the radiative fractions and compare them with the experiments. What I would say is that in real situations, although we've done this detailed study, for jet files, if you are not considering the obstacle effect, one could do well, and with some simple correlations, which I'm comparing with here. And the reason why people are still doing numerical simulations for jet file is because operators need to consider them in connection with the file impinging on surfaces and the environment and the environmental conditions, especially if this happens in a room like this. And then another thing is when we talk about hydrogen, people think about Hindenburg, they think about explosions. So we have done explosions, and we've done explosion modeling, and in collaboration with some industrial partners who do experiments in European project. And so what I'm showing here is experiments and Shell sponsored, and the tests were done in HSE and not far from here, pointing a jet file. This is really a worst case scenario. It doesn't mean it's going to happen all the time. It's a worst case scenario, pointing the nozzle directly on the floor. So you created the immense cloud. You also created that momentum, as well as the congestion underneath this model car. So we were using the OpenFOAM to look at the explosions, comparing the overpressure. And for this part of the work, this one, I must say we did the least amount of modification to the code. What we did do is to implement some correlations, and for hydrogen air mixtures and the modification of laminar flame speed at different concentrations and the Stoke equivalence ratios. So we did a relatively little modification to OpenFOAM for this one. And another thing which we did do for this one is we also got to look at the ignition and how to ignite that in running the code. Sometimes a lot of the development, I don't know, as a PhD student for fluid dynamics, you just spend your time on code modifications. So sometimes what we found is even if you don't modify the code and or with minimum modification, even getting a scenario to run on the computers, it takes a lot of skills, and how to treat the ignition and how to look at the boundary conditions, environmental conditions. So I think a lot of time was spent on that for this one. And then we also look at the other scenarios, and again, using the code to help evaluate the safety distances, and from a storage, mock-up storage room like this, to see at what distances and the overpressure could reduce to 10 kPa, which is the maximum allowed, and without causing too much negative effect to a human being there. And so, and we do say that this is about the stoichiometric region. Around that region, you do get highest overpressure. And again, this is more recent, and for similar situations, and we work together with the Shell Global Solutions, and to using their experiments to guide to test the reliability of our code, and then use the code to model. They did 2 configurations of this barrier walls. And sometimes it's also called blast walls. By putting them around the high pressure cylinders, it could have the effect of mitigating the overpressure. So if there's explosion here, there's a wall between me and you get less impact of the explosions. But in the meantime, and as a fluid mechanic dynamist, you would see, oh, that would also block the hydrogen, hinder its dispersion quickly and into the wide area and dilute. So and also these obstacles, they generate additional surfaces, turbulence, which enhance the overpressure of explosions. So it's not necessarily that the higher the wall, the more walls you have, and the more mitigation effect the walls could have on the explosion overpressure. So we actually evaluated them, and that's what this diagram is about, which I'm not going to details. So, but one thing which we found from simulating this large scale scenarios is that it's difficult to look for 5% agreement, 10% agreement everywhere. And it's the overall trend and the maximum and the timing of the maximum. That's what we are looking at. And it's also those analyses which can help operators and evaluate the safety and define the safety distance for their installations. And as I mentioned, and more recently, we've been working in European project, and now I'm launching my own joint industry project on liquid hydrogen. The reason for that is hydrogen is light, its density is very low, and to store large quantities for the hydrogen economy, you either store them in high pressure tanks, like what you've seen, or you store them in liquid, and store them in liquid form, and it's more. And also with the development of aviation and the marine application of hydrogen, we are going to see more liquid hydrogen storage, and internationally. And but the concern is, and at such low temperature, about 20 K, one would think that it should be safe. It's so cold. But it has its safety implications. As I already mentioned, it expands by more than 800 times with the accidental release. So one thing which we looked at together, we worked with the Air Liquide, which is a French industrial gas company, to look at what's the effect if around the liquid hydrogen tank we put some low band to restrict the spread of the liquid in case of accidents. And rather than it going too far away, and to look at the evaporation, the phase transition, multi-phase flow, and the dispersion in the atmosphere. So we did that work, and that work was actually constituted a part of my impact case study for REF 2021. It's quoted in the REF. The work was also sponsored by Universal Work Impact Acceleration grant. I remember when university asked me to apply for that, I said, no, I'm not applying for internal money. It's my job to bring grants to the university. It's not my job to ask money. Then the university said the impact is worth lots of money to the university. By giving you this money, you generate another small example for the impact case study that could be really important. So that's how this work was getting done. And I would bypass the little bit of modifications. And there's limited amount of data for validation. What I'm showing here is some NASA experiments done in 1984 and for liquid release and they look at the cloud, and we made some comparisons in terms of the visible cloud and the vertical extent of the cloud, as well as the duration of the visible cloud. And so that's the only set of data we could find at that time. But I'm pleased to say now, I think Sandia National Laboratory is trying to do some more tests like that. But initially, the results of the new test will probably be commercial because be confidential, because that's the Sandia new test is sponsored by a Korean KGC in Korea. So don't know how soon it will come out. So with that validation, we then analyzed them, and we will compare them with the different with or without that retention period or that bond you saw in the picture, and to see what's the effect. And it's really the conclusion which we draw from that study. It's really you go to analyze it situation by situation, the atmospheric condition and the size of the bond, because using that bond around the storage vessel, you do limit the size of the cloud, but its duration becomes longer. So it's more confined in that bond, and the evaporation is more slow, dispersion is slow, but it lasts longer. So I talked about hydrogen being requires little energy to ignite. So if the duration is longer, then it's more likely it could bump up with some ignition source. So really the operator's conclusion after doing this work is they would analyze it based on the local situation, but they do consider that the effect of the bond, it has some effect in certain situations. And so these are the more recent tests, and it's done at the DNV Spec Adam. And my favorite was, remember Spec Adam, which used to be one of your under your group, is British Gas, and now it's been resold many, many times, and it's under DNV. They did some tests for the Norwegian ferry companies on jet release horizontally of liquid hydrogen, looking at the flushing, the dispersion, and so these are the test conditions. And we did some simulations, and one thing which we found is that, again, re-emphasize what the statement had made. For such large scales, it's really difficult for you to compare point by point. And you really got to look at the arc, look at the trend. But here, even by looking at the average, I think our predictions are not that good. The reason for that is we made some many simplifications, and especially we were not considering the pore spread and the evaporation, and we were also assuming not considering the humidity in the atmosphere, and those clouds and hydrogen jet come out, they can also freeze the moisture in the air. It can even freeze some oxygen in the air. So we have simplified the physics in this one because it was a quick trial which we did for as a preliminary work for a proposal rather than a research project. And we also did some exploratory study. I call this exploratory study because there's low validation. And we're looking at the liquid hydrogen jet and coming out and ignited. We look at the jet files and whether it's in the case of without wind or the next one with wind, and so it's blowing more horizontally. We are hoping in the new joint industry project, which will start next year, we'll be able to do some validation. And this is some preparatory work to see that we got the potential to do it. But and to do it properly with validation, we need some phase development. For example, in this one, we are bypassing the phase transition. We assume instant flushing and cold hydrogen gas, cryogenic gas in 20K, rather than liquid going through the flushing process. So even in the safety domain, I hope when looking at my talk, is some student may say, I'm not trying to grab students from here, but what I want to say is that even it's reactive flow, and in our topic, we do need a lot of people with a fluid mechanic background and with solid fluid mechanics theory and the numerical models, especially. And my team, I'm always looking out for postdoctors who's interested in code development. And I don't take students, postdocs who just want to use the code. Students I may take on, and but for postdoctors, they all have to develop codes, and they don't have to have combustion background. Just through the mechanics background, they will learn combustion very quickly. And so vapor cloud explosions, this is again from cryogenic release with simplifications. And so it's an illustration of the overpressures and the temperature, the evolutions. So the concern for the vapor cloud explosions, this can happen, for example, when you have liquid hydrogen bunkering, and for example, at the airport or from ship to shore, and when we have large boat of liquid hydrogen come from the Far East. And in those environments, there could be semi-confinement. And there's very little knowledge about the likely overpressures, about which can result from overconfinement and from semi-confined or confined environment. But some tests done in the in the European project, PRESTI, which I was a partner, we did find that, the test did find that the overpressure shoot up and rapidly with the confinement, with the congestions, and for vapor cloud explosions. So, and these are comparisons, which I won't go into detail. So a quick conclusion about the hydrogen work, and before I move, give a quick introduction about the firewall, which we are doing now. Is we have developed the codes and for various scenarios and related to hydrogen, and this is a growing area, and where we have serious scale shortages. We have scale shortages, and not only for people to do risk analysis and for industry, but also for skilled and researchers who can develop codes and modify codes and to tackle some challenges. Some of the challenges, if you focus on the fundamentals, there's really a lot of things you can do, but not every researcher is able to dig into those fundamentals. And to finally, just a quick run through the Living Home Trust funded project and on firewalls, and with global warming and wildfires are becoming more and more of a concern. And even for the UK, we've had wildfires in the Highlands, and we also had bushfires and peat fires. And so what we are looking at firewalls, this is a special phenomena, and which occurred in the 1921 famous earthquake after the earthquake in 1921 in Japan. And the swelling flows and came from the wind around the buildings, driven the fire shoot up very high. That's why in the media, they also call such firewalls, they call it fire tornado. And so what we have looked at, we try to simulate L-shaped firewalls, and which happened after that experiment. And they had an initial firewall with type 1, and then a firewall in the middle, and a firewall fell downstream. So and they did. Some Japanese researchers did a reduced scale experiment. So what we tried to do is to simulate that experiment, developing models. And what we have started, but we use a file form I should mention FileFOAM, which is a code, which is a solver, file simulation solver within OpenFOAM. And my group has been sponsored by FM Global for many years, and to add submodels for combustion and soot and radiation into FileFOAM. So this is the application of that. This is an application of that, and the FileFOAM code which we helped to develop. And what we did was we did add this vorticity equation. I mentioned this because the next speaker will be talking about vorticity. I'm looking forward to it. We don't have to add this. It's already in OpenFOAM. But the reason we have to add the equations in is we got to get the code to output these different terms to a file so we could analyze it. Otherwise, we wouldn't need to do it. So we wrote this equation in there, so we could output all this to different files. We can plot and analyze it. So these are some of the, I think that's my last slide. I know I'm running out of time. And so we look at the scenarios. So what we found is that the type 1 and the type 2 firewalls, as you can see here, they are primarily generated due to the baroclinic torque. And by printing out those terms from the vorticity, while the type 3, which is the one in the middle of the L shape, that's generated due to tilting, traction, and stretching effects, and which is why we had and without those detailed parameters, just from the experiments or from observation, we wouldn't be able to come up with this conclusion. So we did all those, added those equations and looking at the terms, we were able to come to this. So at the moment, this is still a much reduced scale, and we use large AD simulation with relatively fine grades to look at the terms. And we have another year in the project, then we have to try to speed up, because to look at the really large scales, we probably will still have to go into runs eventually. We are still trying to hang on with the LES for a bit longer, and then before we move to large scale applications, looking at the limiting conditions and for transition from a file, word file to file or a file will. So that's end my presentation.